Here's a video on pKa's and pHs and how they relate, like we discussed earlier today in recitation. And so I thought rather than just sending out an email, it would be easier to do this video for two reasons. One, just because it would be easier to see, and two, I feel like emails documents are more of a doctrine type thing, and I want to make this clear that what I'm about to explain is one of my techniques and one of my tricks in understanding what a molecule's overall charge is going to be at a certain pH when considering all of its pKa's of its functional side groups and whatnot. And so some caveats, the pKa and pH scale cannot be conceptually overlaid as it's going to seem like I'm laying out in this video, so those are something to keep in mind. There are some gaps with this conceptually, but in terms of the technique and kind of the patterns and the tricks of understanding what's going to be protonated, what's going to be deprotonated at certain conditions has always held true throughout my years in OChem and going through biochem. I haven't seen an instance where this hasn't gone through. So let me walk you through this. What I've got here shown is a dipeptide, DK, Donkey Kong, formerly known as aspartic acid and lysine. Aspartic acid or aspartate, you're going to hear both of those for those acidic ones. That's just a nomenclature thing. Remember, we take off the ic on acid and replace it with ate for when it is deprotonated, and so you can hear aspartic acid, aspartate, either one of those, and they go for all those acidic amino acids. Then we have lysine. And so I've got this drawn. I don't have the stereochemistry indicated because we're not concerned with that right now. I have it drawn as if it's completely neutral. I'm not specifying any conditions. I'm not specifying any pH levels or anything at which this molecule is drawn. I'm just drawing it for what it is. And so what we're going to do now is we're going to explain first what pKa's are. So let me first throw up the pKa's of this molecule, and to be more accurately correct, I did look these up just barely to make sure that we're accurate. So we have a carboxyl group, we have our C terminus over here, we have on lysine, we have this amine group, and so for the pKa of ammonium, it's going to be, let's see, it's going to be 10.5. And then we have a carboxyl group on an aspartic acid, which sits at about 3.7 for its pKa. And then we have the N terminus, the amine group, and that one for this specific amino acid is 9.6. Don't get confused by me getting too specific on these. Again, Dr. Andrus, he specifies that all he expects you to know are the pKa's of carboxylic acids and ammonium, which is 5 and 9 respectively. There may be some other ones he might give you, so it's good to know how they work, and you'll get more into it in biochem, but with these N and C termini, they do vary in terms of their pKa's based on what R groups are on to those specific amino acids, but again, we're not going into that much level of detail. And as you can see, it's still generally the same. The N terminus is around 9, the C terminus is a little bit lower than 5, but we'll say 5 generally on tests unless he explains further. I guess we'll await any of his instructions there. But for this demonstration, I'm just going to use the actual pKa's as they exist. So first, let's define what a pKa is, and let's start by understanding what a Ka is. So a Ka, if you remember back in Gen Chem, is an acid dissociation constant. Acid dissociation constants are basically referring to the propensity of a hydrogen to leave a functional group. So as the acid dissociation constant increases, there's a higher propensity or likelihood of that hydrogen being dissociated, meaning that it is, we would say, a more acidic molecule, because strong acids are those that dissociate easily, strong bases are vice versa. but we're just dealing with the Ka here. So acid dissociation constants, the higher you go, the stronger the acid, right? So that's what an acid dissociation constant is. So when you take the pKa, whenever you add a p on here, you're taking the negative log. And so essentially what that does is it is just going to reverse the trend, is what you can think of. So the lower the pKa, the stronger the acid, because it's just an inverse, it's a flipped trend. Just like how we have pH. pH is a measure of hydrogen concentration. The more concentration of hydrogen ions that you have, or protons, the lower the pH, we say. The more acidic the solution. So kind of the same trend here. The lower the pKa, the stronger the acid. So that's what a pKa is. It's just referring to how strong the acid is, or how likely it is to give off that hydrogen. Okay, and that's what I've labeled here in blue. I've labeled the pKa's for all of the functional groups here. So now we are tasked with the assignment of knowing what certain conditions are, and by conditions we're just talking about a certain pH, and we have to decide how are each of those functional groups going to be affected, and what's the overall charge of the molecule going to be. So let's start out at a low pH. If we say a low pH of 7, what is going to exist here? So the rule that, or not the rule, sorry, the trick is what I want to say is a better term for this, is that you want to first know what your pKa's are, and then you want to look at the conditions. If the condition is below the pKa, I would say it's on the acidic side of that molecule. If the pH is above the pKa, it's on the basic side of that molecule. It kind of goes along with the trends, right? The lower the number, the more acidic. The higher the number, the more basic. And so let's take pH 7. Oh, sorry, I said we're starting out at a low pH. Let me redo this. pH 2. So low pH, pH 2. We are now going to be in a very acidic condition. So we have a lot of hydrogens, right? Low pH, high concentration of hydrogens or protons, meaning that things are going to most likely be in their acidic forms. And their acidic forms, remember what those mean relative to the pKa's. The pKa's are always specific for one proton dissociation. And so we know that for carboxylic acids, generally it's 5, and it refers to the carboxylic acid. The more confusing one is ammonium with an M on the end. That is the pKa of 9. It is not ammonia. If you were to say what the pKa of ammonia is, that's like in the 30s. It's very, very high. Not going to dissociate very easily, right? But ammonium is. And so when we have these acid dissociation constant, or pKa's around here, like 10.5 and 9.6, those are referring to ammonium, not one of the hydrogens as I've drawn it here. Okay, so pH of 2. Let's start over on the N-terminus. We are at a pH of 2. We have a pKa of 9.6. We are on the acidic side of this pKa, meaning that this functional group is going to retain its acidic form. So we can draw this. This is ammonium. Let me just finish the peptide here real quick. Ammonium is tetravalent, even though it doesn't have 4 protons. That's fine. It's tetravalent. That's the main thing. And we know it's going to be positively charged because we're on the acidic side. There's more protons. It's going to exist in its acidic nature. We now have aspartic acid at a 3.7. 3.7 pKa. Okay, let's look at our conditions. Still at a pH of 2. We are on the acidic side of 3.7, the lower end, meaning that this functional group is going to retain its acidic form, which is actually how I've already drawn it. So we'll just replicate that. These amide bonds are not going to be protonated or deprotonated. So now we're considering our lysine R group up here, 10.5, definitely on the acidic side. So similarly, we are going to be protonated as well. And then we have finally our C-terminus, and we are just barely on the acidic side, but we still are, and so we would say that it's going to remain in its acidic form as OH minus. So now let's consider this molecule. We have a positive charge here, a positive charge here, and that's it. And so we would say at a pH of 2, DK has a net overall charge of positive 2. So now if we were to change our conditions, let's go to physiological conditions, pH 7. Let's do this again. So pH of 7 now, let's start over on the amine side, the N-terminus. We are still on the acidic side, so we're going to keep the amine protonated. Just drawing this out again. Okay. Now things change a little bit. With aspartic acids, our group, we have the pK of 3.7, and if we look at the pH of 7, our conditions now are more basic than what the pKa value is itself. So if it's more basic, is the R group going to exist in its acidic form or its basic form, basically? Its conjugate base form is what we want. So O minus, it will be deprotonated because now we don't really have enough hydrogens to keep it protonated. We're at a pH of 7. It's on the basic end of this specific pKa. So now we'll go back up to lysine. We're going to keep this one protonated, very similar to the other one. And now we are going to consider this guy. We are still on the basic side of 2.18, and so this will also be negatively charged. Okay, so at a pH of 7, what do we have? We have 2 positive charges, 2 negative charges. Thus, we are at a overall charge of 0 for this molecule at pH of 7. So we'll go to the last extreme here. We'll go to a pH of, let's go like 13, very basic. Okay, so let's start on the N-terminus here. We have 9.6 as our pKa. The pH of 13 is a higher number in value than the value of 9.6. Thus, we would say it's on the basic side of that functional group. And because it's on the basic side, it's going to exist in its basic form, which is actually how I've drawn it, with its proton lost. So it just remains as the amine there. So now with the acidic, well, we already said that it was deprotonated at a pH of 7, so any higher, I mean, it's going to remain deprotonated. And then we'll consider this guy up here, lysine, pK of 10.5. Our pH is at 13. And so we will actually still have that one, or not still, but like the N-terminus, this one will be neutral. It will lose its proton because the conditions are more basic than the pKa itself. And then lastly, this guy is deprotonated. So now what do we have? We only have 2 negative charges, so our overall charge of the molecule is -2. So I hope that helps a little bit. I have repeated a lot to try and hopefully just get the patterns in your brain. Again, this is my trick of doing this. This has worked every time. Every time you are dealt or given a long peptide or an amino acid, the first step is to establish your pKa's, to know what those are. He'll give those to you, or you should just know that carboxylic acids are 5, ammoniums are 9. And then look at your conditions and consider the conditions for each pKa independently. Again, I want to put in a plug here. Don't get caught up in if the molecule is drawn, don't get caught up in how it's drawn and let that dictate or confuse what acid or what hydrogens are going to leave and what not based on how it's drawn. Just remember what the pKa's correspond to and you'll be good. So once you've established your pKa's, look at your pH, that's your condition, and now put that number and relate it to the pKa's. If the pH is lower than the pKa, that functional group will retain its acidic form because we have enough protons in order for that to do so. If the pH is a higher number, or it's to the right, I would say, of the pKa of a molecule, then we are on the basic form, or the basic side of that molecule. We no longer have enough protons. It's going to exist in its conjugate base form, and then you know how it looks and you know what charge. Don't get caught up and memorize at certain pHs or being on one side or the other will be positive or negative charge. That'll mess you up for sure. As you can see, being on the basic side of an acidic group is going to make it negatively charged, and being on the basic side of a basic group is going to make it neutrally charged, as you can see here with what we've done. But I hope that helps. Let me know if you guys have any other questions, and we will talk to you later.